All right, 2.7. So in this section, we want to consider situations in which two or more quantities can be related to each other. Usually we're talking via an equation. And when we do this, we're going to go ahead and consider all variables to be functions of time. And you'll see what I'm talking about in just a second. So even though you haven't done a problem yet, and in some ways what I'm about to say won't mean anything until we do an example, I do want to go ahead and give you the goal and then sort of the key flow, the problem flow, the steps that we're going to follow. So our goal in these sections is to compute a specific derivative or rate of change, if you will, at a specific, let's say instead of at a specific, let's say evaluated at a specific value. And you'll see what I mean. And so the key flow is going to be step one. You want to establish a relationship among your variables, and this is usually going to happen via an equation. Step one is looking for an equation or equations plural. Step two is you want to differentiate, and you're differentiating with respect to time, t. T is going to be our main variable. Remember, we're assuming everything is a function of time. Everything is a function of t. And then three, after you've done those two things, only after you've differentiated, will you plug in the specific numerical values. Okay, so again, look for a relationship, take derivatives, plug in the specific values. That's the flow. So let's dive in and do an example. I've posted this blank handout on Teams. Highly encourage you, if you haven't already, pause the video, go print off a copy of this, and then come back and work it out with me on your copy. So first problem, we've got a balloon. We're going to assume our balloon is in the shape of a perfect sphere. And we're also assuming that it's being inflated at a constant rate of 20 cubic inches per second. And so I want to mark the word inflated. It's being inflated. That is a word that has to do with volume, right? We're changing the volume. Inflation is change in volume. So that's the first sort of key observation. All right, and so the question that we're asked is, how fast is the radius of the balloon changing at the instant the balloon's diameter is 12 inches? And so you're used to thinking about time as, 1 second, t equals 1, t equals 2, t equals 3. That's all fine and dandy. But what I want you to realize is that when we've got this balloon and it's getting bigger and bigger and bigger, there is a specific moment in time when the diameter of the balloon is exactly 12. And we're going to specify time like that, not at t equals 2.6 seconds, but rather the moment when something happens. Okay, so I'm interested in the volume of my balloon, and I'm ultimately seeking, let's write down that our goal is the rate of change of the radius. How fast is the radius changing at the instant? This is the instantaneous rate of change of the radius with respect to time. This is dr dt, and then at the moment that the diameter is 12 inches. And so we can say the derivative evaluated when d equals 12. Remember, this means the derivative of r with respect to t. The bar and then this part means take whatever that derivative is and evaluate it the moment d equals 12. So that's my goal. I'm looking now for a key relationship, and I'll go ahead and write this down for you. So I'm looking for a relationship between what I know something about. I know something about the rate of change of the volume, right? It's inflated at a constant rate of 20 cubic inches per second. This is talking something about volume, and then I'm interested in something about the radius. So I'm looking for a relationship between volume and radius of a sphere. Well, there's a formula, you know, right? The formula is V equals 4/3 times pi r cubed, or I'm going to write this as V equals 4 pi r cubed over 3. Same thing. I find that easier to work with, so we'll slide that up. All right, so that's my key relationship. The other key relationship is I'm given something about the diameter, but I want something in terms of the radius. And so another key relationship is that the radius, 2 times the radius, is in fact the diameter. So we're going to need that. And already you can begin translating in your mind. Okay, the moment the diameter is 12 is the same as the moment that the radius is 6. So we can write this. This is equal to the rate of change of the radius with respect to time evaluated at the moment the radius is 6. So feel free to make those changes. So now we're going to copy this formula. I'm going to go ahead and write it down again over here. And here's what I want you to realize. This is a formula, and every variable, pi is not a variable, by the way, that's just a constant. Every variable you're to view as a function of time. As time passes, the volume of the balloon is changing. It's a function of time. As time passes, the radius of the balloon is changing. It's a function of time. And so you can take the derivative of this expression with respect to time exactly the same way we did in the last section using implicit differentiation. We're going to use implicit differentiation here. Everything is a function of t, and so let's do it. So on the left side, when I take the derivative of v with respect to t, I just get dv dt equals, on the right side, these are just numbers, so I have the 4 pi thirds times, I'm taking the derivative of r cubed with respect to t, so I get a 3r squared times dr dt. And at this point you should let out a little bit of excited yell, because you actually see the thing that you're looking for the very first time. There's dr dt, and it's related to dv dt. Okay, so far so good. So let's think about what we want here. So I'm going to use, I don't know, this pink color. This is what we want. We want dr dt, and I'm going to mark it here. Okay, that's what we're after. And I'm seeing that I want that all the way right here. How fast is the radius of the balloon changing, right? That's telling me that I want to figure out the rate of change of the radius with respect to time. I also see another rate of change. I see this dv dt. That just shows up here, okay? And it's an important part of the thing that I want. And I want you to look at this line. The spherical balloon is being inflated at a constant rate of 20 cubic inches per second. I want you to realize that that line that I just underlined, that's telling you what the rate of change of the volume is. This is, inflation is change in volume. This is saying that the change in volume, it's constant. It's never changing. It's always 20. And so you can actually plug that in. You can replace dv dt with 20. And so you know 20 is equal to, let's cancel these 3's. 20 is equal to 4 pi r squared times dr dt. And now you realize I don't just want dr dt. I can solve, and I can get that dr dt is 20 divided by 4 pi r squared. That's all fine. This is the same as 5 over pi r squared. That's great. What we're specifically looking for, though, is dr dt evaluated when the radius is 6. And so from this formula, we can finally finish it. We can say, okay, look, dr dt evaluated when the radius is 6, that's just going to be 5 over 36 pi. You can just plug in r equals 6. So before I end the video, I want to go back to the top and look at the 3 things. We wanted to establish a relationship among the variables, maybe more than one relationship. I want to take derivatives of my key relationship with respect to time. Only after I've taken derivatives do I plug in the specific numerical values that I'm given, such as the 20 and the 12. That's what we did. We found a relationship. we took derivatives with respect to t. We used implicit differentiation. We got here. Then I plugged in this value, and I solved for this part, and I finally ended by plugging in r equals 6, and I got what I wanted. So that's the first of, I think I have 3 or 4 of these examples that I'll do with you. So I'll end this video here, and in the next we'll just do another example on the next page.